Welcome to our NPTEL lectures on DC microgrid and the control. We shall continue to do our discussions on DC microgrid stabilization strategies. We shall today see that the passive damping method, and in subsequent classes we shall discuss about the active damping method. Now, as we have seen in previous lectures, there are so many power electronics converters and their impedance matching is an issue, and thus from there we require to do a lot of tuning. So, for this reason power electronics converter at the, we have already told it several times that a power electronics converter at the basic building block of this microgrid, and especially this renewable energy based DC microgrids. These DC microgrids mainly this energy resources that consisting of the renewable energy and the storage element interfacing with the converters, and the energy storage interfacing with the converter and the constant power loads, and the uncertainty associated with these energy resources because of the varying natures of these renewable energies, and this system becomes highly nonlinear. All of a sudden load may change, that was a problem in case of the typical power system. Now, you have a problem with the battery's voltage balancing, you have a problem with the variable irradiation and the temperatures and the wind of the solar. So, these are many parameters which has to be catered into the microgrid, and thus system becomes highly nonlinear. And of course, we can write it out the average model once because you have a power electronics converters and you have a one switching state and another switching state, and based on that we can write it down the average models. And when you have an average model, then you apply a linear control technique, and that will be most preferred solution will be the PID controller. So, the proportional integral and adiabatic controller techniques are generally applied while considering the linear model, are insufficient to regulate the DC bus voltage, because system is highly nonlinear, and when you make it average model, PID controller does not gives you satisfactory results. The DC bus voltage to stabilize the DC distribution systems in interface with the constant power load and the uncertainties. So, we require to design the controller taking all those nonlinearity into the account, and thus under this situation the design control must have sufficient robustness. Robustness means the system is very much stout in the any change of this one state to the another state. So, state change will not affect its positions of the stability, that is called the robustness, and robustness to ensure the stability and the performance of the system. Since impedance interaction is the root of the instability problem, so that is the change of impedance, because you are tracking the MPPT, your voltage changes, current changes, and thus there is a change of impedance, and sometimes your load changes. So, thus the impedance interaction is the root cause of the instability problem in source loads interconnected system, and stabilizing a constant power load, because once voltage dips its current increases. So, it is quite nasty kind of entity. So, CPL system typically requires a reshaping of the source output or the load out input impedance, so that you can control the flow of current into the system. To ensure this, we can go for that stabilization by the passive damping, but of course, it is a less efficient system. Let us see how it has been done. A passive stabilization method uses a passive component such as resistors, capacitors, inductor to improve the stability. Mostly required to damp out the oscillation. You require to make the system you have to visualize the system as a second order system by the reduced order model, and thereafter you with the effect of the dominant pole you try to design the specify the oscillation by the proper damping. Compliance with the electromagnetic interference standard, because there is a challenge once you are having this kind of issues. So, generally once you have sustained oscillation, then generally you have a huge problem of EMI EMC, and what happens generally once you suppress one entity, generally you will find that you have aggravated another entity. So, you have to keep into the mind that while you are damping, that it may increase your electromagnetic interference standard, because what happens when a wave gets reflected, when that will be the cause of the EMI, when a wave electrical will be reflected when there is a mismatch between the impedance. So, for this reason this will you will find that more mismatch into the once you are putting a passive damping, you may introduce a little more mismatch into the impedance, and thus it may aggravate the cause of the EMI. But you have to keep in mind, ultimately you have to find it out the optimal solution, and you have to see the standard of the EMI, so that you can have a little flexibility here or not. This EMI standard usually require the insertion of an EMI filter between the switching power converter and its use. Generally you have different, that itself is a big chapter. Generally you have a conducted emission, and that will have a common mode noise as well as the and the radiated emission. Generally conducted emission can be reduced by the EMI filter. There is a XX filter that is for the common mode, and that is for the differential mode is called XY, and that filter will try to reduce your conducted emission. And also you will have a problem with the radiated emission that required to be addressed by low DVDT and low DIDT. So, passive damping is also widely used to minimize the LC filter impedance picking. So, that is something can be done. So, once you have introduced a proper damping in a second order system, your peak overshoot will decrease and all those issues will pop in, and thus proper designing of the LC filter will reduce the picking. So, let us consider this figure 1, and it shows a converter source system with an EMI inserted between where a single stage LC filter is assumed for the simplicity. Now, you have a source, you have a CPL. Now, what happened? This is the filter, and since it is assume that there is no resistance here. So, any step change or any change will have a sustained oscillation into the system, and thus we require to provide the proper damping. So, please note that the input impedance of the LC filter dips at the series resonant frequency between the filter inductor and the filter capacitor. You know the Q factor, and based on the Nyquist criteria, instability between the source filter may occur if filter input impedance becomes lower than the source output impedance at this frequency. So, this is a cause of instability. So, you have to keep in mind this is a very one of the thumb rule of designing the filter. So, you have chosen a particular switching frequency, and so you may one layman kind of question sometimes asks, so what is the frequency in a DC microgrid? Because all these DC to DC converter are switching device, thus it has got a operated at a particular switching frequency, and you have required to filter out those high frequency. And while designing the filter, you require to remember this Nyquist criteria very well. So, the filter may the based on this Nyquist criteria, instability between source and the filter may occur if the filter input impedance becomes lower than the source output impedance of that resonating frequency. And if the switching frequency becomes the resonating frequency, then there is a gate hazard. So, for this reason the LC filter with the constant power load and the passive damping, it has been shown. So, this part is a CPL and this part is a filter, and since you may not have fulfilled that criteria, and for this reason you have added one RC network to tamp out the oscillation. And thus what happened, this is called the passive damping. Since some amount of current will be sinking here, so efficiency of the system will be lower, but you will be get rid of the effect of the instability. So, and assume, please go back to the figure, this is C1, that is a filter capacitor, and this is a damping capacitor C2. Assuming that C2 is much greater than C1, at higher frequency the impedance of C2 will be very small and the total resistance connected to the output of the filter will be given by the parallel combination of R and the CPLD load, that is RL, and thus having effective R will have minus sign comes from the CPLD. So, R into RL minus this one. So, looking at this relationship, if RL is much greater than R, the LC filter will have a negative damping resistance and the filter definitely will oscillate. So, that is the challenge here. So, this will have a sustained oscillation. Now, for this reason, or therefore, to ensure the system stability, the magnitude of the damping resistor must be lower than the magnitude of the load impedance as noticed by the this person Brittlebrook in his impedance matching criteria or the impedance stability criteria. The capacitor C2 should have lower impedance than R at the resonant frequency and be bigger value than the filter capacitor in order not to affect the cutoff point of this RL filter. So, that is another criteria of this Brittlebrook's impedance. Now, let us see that analysis of this LC filter with the we have to refer back to this figure. So, figure 2, viewers are requested to refer that figure by sliding this A. So, this is the analysis of the LCL filter with the CPLD passive load damping, and to analyze the circuit it is undertaken by considering the input and the output transfer function, that is your VCS by Vs of this figure 2, and thus what you can write this transfer function, you can see that it is a third order, but you can reduce it by second order by the dominant pole method. So, you have a overall transfer function like this, and the purpose of this damping resistor R here is to reduce the output peak impedance of the filter at the cutoff frequency. So, thus it will be flattened. So, overshoot will be reduced. The capacitor C2, generally it blocks this DC component or the low frequency component of the input voltage and avoids the power dissipation on R. The output impedance ZS of the filter and damping network can be expressed as ZS equal to SL 1 plus SR C2 by S cube LR C1 C2 plus S square L C1 plus C2 plus SR C2 plus 1. The transfer functions represents a 0 and 3 poles. So, here you got a 0 and you got a 3 poles, where the 0 and the first pole flow close to the each other to the frequency what it is given by, that is the omega, that is 1 by R d into C d. Please refer back here in the figure number 2. So, the other two dominant pole will be at its cutoff frequency, and that is your natural frequency of oscillation of this filter, that is under root of L C. The damping resistors with the series L, if you connect, then efficiency will be the catastrophe, would decrease the converter efficiency. Casualty will be the efficiency, because series current will flow. Since it must pass all the DC current, so there will be a loss. So, you cannot add in a series, you require to add in parallel. While damping resistors in series with C1 will seriously degrade the attenuation characteristics as well as the efficiency, since it must essentially pass entire AC current to component. So, ultimately filtering effect will be a catastrophe, THD will be a catastrophe if you add a resistance with C1. And for this reason what we do, we add one practical solution for damping for the input filter as illustrated in figure 2. The DC block capacitor C2 is added in series with the resistance R. So, that is the case. So, consider a simplified model of the DC microgrid and the passive damped circuit with the constant voltage and constant power load, that is the CPLD, and this is the filter part of it, and you will add extra damping resistance to damp out the oscillation, that is RDCD, and the simplified method of the DC microgrid with the parallel damping. Now, let us now come to the stability condition once you have damped it. Of course, you expect that stability will be improved. In order to improve the stability of the system, the passive damping circuit was added to the system and simplified the circuit model as shown in the figure, that is the figure 3, this one. The method of determining the damping resistors and the damping capacitor can be derived as follows. So, it is L di dt is the voltage across this inductor. This, please refer to this figure, this element before the filter we say it is the source EC. So, you write this equation here. So, L di dt equal to EC minus the voltage across the capacitor, that is UC. Again the current sinking into the capacitor is dB dt, C dB dt, that is C E du is U C E dt equal to L E minus this difference U C E minus U C D by R D, and since it is high frequency we assume that the higher capacitor is shorted, value of the C2. They are at U C E by R minus C P L D by this capacitor voltage. Ultimately what you can have is your C D T U C D equal to U C E minus U C D by R D. So, this is the equations what you have, and thus from the equilibrium point of view we can find, solving those equations, that L E equal to U C E by R plus P C L by U C and E E equal to U C and U C D equal to E. So, linearizing these equations at the equilibrium point, and the equation is organized in a matrix and matrix form and given in the file. So, this is the overall transfer function with this filter with the damping network. So, these are the state variable, that is the current to the inductor. Thereafter, you have the voltage across the capacitor, differentiation of the voltage, rate of change of voltage across the capacitor of these filters, and rate of change of voltage of the capacitor across this damping resistor. So, what you can see, you can write it down the state space equation, and where 1 by R minus CPL by UC square equal to 1 by RL. So, this is one of the constraint, and this RL is a small signal equivalent load impedance. So, that is something we take it as a RL, load impedance. Now, while the stability analysis, so we can spread these equations from this state space equation, we come to the transfer function model, and thus we get this is the characteristics equation, this is the denominator essentially. This is a characteristics polynomial, and we have to analyze the stability analyzing this characteristics polynomial. So, it is S cube plus 1 by C 1 by R d minus R L. Please note that R L is quite small, thereafter 1 by C d plus R t into a square, plus this is the damping part, since it is a coefficient of S. So, L by C is plus C into R L C d into R d, and that into S. Thereafter, this will be essentially the damped oscillation part omega d, and thus we apply a simple criteria that you have studied in your basic control system in your BTech level, that is the Raoult-Hurwitz criteria. In equation 7, and the necessary sufficient conditions will be the sign change in the rho, and thus we rewrite the Raoult-Hurwitz criteria here. So, what you get here, C d into R d should be less than that R L into C d into C, to having a stability criteria to fulfill. C d into R d should be greater than L e by R L, and also you have C d plus C by C in bracket 1 by C d R d minus 1 by C d R d R L into C d R d minus L e R L, it should be greater than 1. That is equation number 9, and where R 0 will be where R 0 will be under root of L by C, and this n is a ratio of the C by C e. So, that is something the notation will be followed, and based on that we have to have this criteria, and based on that you will design the value of the C d and the R d. So, you fix up the C d, because generally what happens, C d comes in some numerical values for 47 microfarad or some other values. So, then what happened, since we require to fix the value of this R d, and thus you get a little range, extremely sorry, first you fix up the value of the C d. Once you fix up the value of the C d, thus you get a range of the R d, and it is your task in simulation also, you put that values of the R d and check because in a real hardware setup you may not do that heat and trial, and for this reason you take a range of the R and you swipe out the value of R and see that where it gives the best response. But of course, your theoretical aspect will mismatch, there is a lot of parasitic entities that will come into the picture, but then we have to take care of this, eliminate or account those parasitics in your hardware. So, that what I can say is that the damping of the system changes with the value of R d. The optional damping of the system is obtained by R d satisfying the following equation, that is R d equal to R 0 by n under root of n plus n 2 n plus n 4 by 2 n plus n 4, where n is the ratio of C d by C, and thus this is the value of the R d you will get, and from this 9 and 10 we can derive the condition of the stability, that is R 0 by R L, this ratio should be less than n into. So, you can take this these two equations and combine. So, 2 into n 2 2 into n plus n 2 by n plus n 4 into 3 n plus 4. This is the conditions while choosing, because you have chosen a filter based on the switching frequency. So, your value of L E and C E are fixed, and so steps will be the ones you have fixed, then you come across this relay, then you will fix up the value of the C D. If you have chosen that capacitor voltage to be maybe actually 0.47 microfarad, and you choose this capacitor as 47 microfarad. So, it is actually 100 times higher. So, n value is 100, and accordingly you will have a R d, and thus you come into the conclusions, and you require to design properly what should be the value. Please note that this capacitor C d should not interfere, and that should be around 50 to 100 times higher than the value of the filter capacitor C, then only this will work fine. Thank you for your attention, and what I can say in here, that this characteristics you have to write it properly. Thereafter, this is the steps, again I am reiterating, this is the step. Thereafter, you come to the transfer function. Students should be very much aware of converting your state space into the transfer function, then you get the transfer function, and thus you get the criteria, and you see the what should be the stability of the system by equation number 11. So, thank you for your attention, and in next class we shall see that active damping maybe and some other cases of the passive damping. Thank you for your attention. Thank you.